Okay, class, we're back to again discuss net filtration pressure. We ended it with the last one, so let's start over again to be sure you have a fairly good understanding. Okay. Net filtration pressure. There are many things that go in and out of capillaries, gases, liquids, everything. But this calculation we're going to do is called the net filtration pressure, and it's for water. Good fresh water ought to come out of the capillary at the arterial end and then come back in later, bringing good stuff in and out. Starling's law of the capillary states that as much water as you put out, you need to bring back in. As much water as you take out, you need to bring back in. If you put more water out in the capillary, in the tissue area where the capillary is, than you pull back in, you will get edema. This edema will be called angioedema or vascular edema. If you push more back in that you bring out, obviously it would get dehydrated in here. So idealistically, you should put as much out as you bring back in. So let's look at that. All right. By international convention, net filtration pressure equals the amount of fluid out of the capillary minus the amount of fluid re-entering the capillary. Generally, it's calculated two locations, at the arterial end, which what they do in the book, and the venule end. At the arterial end, you put the fluid out. At the venule end of the capillary, you bring it back in. The forces out of the capillary are the hydrostatic pressure of the blood. That's the water, hydrostatic, coming out. That's pretty much the mean arterial pressure there. Okay? That's a push-out force. But also at this end, you have a suck-out force. Osmotic pressure is a sucking pressure. Remember in ANP1, hyperosmotic, isoosmotic? So solutions outside here will suck water out. So the two forces out of the capillary are the hydrostatic pressure of the blood and the suck-out pressure of osmosis. The forces into the capillary is the water out here trying to push back in. And the osmotic pressure of the blood, its solution inside here trying to suck water back in. So those are the forces out and the forces in. So now we come and we do the calculation. We want to do a calculation at this end to see what happens, and at that end and see what happens. All right. So here's my calculation. Net filtration formula. The NFP equals to the force out of the capillary minus the force into. The NFP therefore would equal the blood hydrostatic pressure, which is the push out, plus the interstitial fluid hydrostatic pressure. That's a pull out, but both of them out, force out, minus the interstitial fluid hydrostatic pressure, push in, fluid outside the vessel pushing in, plus the blood osmotic pressure, which is a sucking pressure pulling you back in. So using symbology, NFP would equal to BHP plus IFOP minus this. You can see here. Now, let's use some numbers based upon, let's say we'll use these numbers from that text. Okay. So we said we would calculate at the arterial end and the venule end. So at the arterial end, we're saying that 35 is the blood hydrostatic pressure. Now, where did we get that from? Right here. We said that as you entered the capillary, you had a 35 because of the arteriole. Okay? Then, so we'll go back. So we're saying then that 35 here plus a 1. What's the 1? That is the osmotic pressure of the interstitial fluid, this solution out here sucking out, minus a 0. The 0 is the hydrostatic pressure pushing back in. Now, I'll explain why it's 0, because there is water out here. I'll explain that in a little while. Let's keep it at 0. Plus 26. The 26 is the blood osmotic pressure. See, the blood osmotic pressure is higher. It has a better solution. And And one of the reasons it has a better solution, it has the plasma proteins and some other things. We'll talk about it another time. So if I do my calculation, you see here, I have a 36 minus a 26, and that's a 10. See this, I rearranged this in a different algebraic way over here that you can put things together, out minus in. At the venule end, we come in and we have this, the net filtration pressure at the venule end. Okay, we went to a 17 instead of a 35. Why did we do that? Let's go back to this picture. As you exit the capillaries, you see, and go into the venule end, exit here, you're down. Why? Because of resistance. Remember, resistance removes things. Resistance removes things because of the length of the pipe and the narrowness of the capillary pipe. So we're exiting with a 17, okay? So here we are exiting with a 17. Now everything else we're going to keep the same. So the thing that happened was you had a drop off of pressure because of resistance. So you had a minus 8. All right. So that violated Starling's law of the capillaries because, in fact, you put more out than you brought back in. And if you don't, now this is happening every millisecond. So if you don't do something fairly quickly, then you would have edema. You'd have edema because you see what I'm saying here. All right. So what's making the adjustment? The lymphatics. The lymphatics. So let's go here. If you recall, when we did the lymphatics, which you've already studied on, we said the lymphatics did three things. One, it did immune. The other thing, it brought lipids in from the intestine and carried it through the thoracic duct. And the third thing, to adjust fluids in these tissues. Now we're bringing that in. These lymphatic vessels are allowing the fluid to enter here, which if you remember, the lymphatics will ultimately enter the bloodstream at the right lymphatic duct or the thoracic duct. So the lymphatics make the counter adjustment. Now, along that same line, I want to bring this up. Remember I said that this was a 0, that there's fluid outside here, but it's a 0. Why? Because the lymphatics are constantly sucking. It's like a vacuum. So there's water there, but it's at a negative because lymphatics will have a constant suction going. A constant suction going. So even though it's water, it's at a negative. Now, what will happen is that, let's say we're looking at the lymphatics in your arm. If you bend your arm, the lymphatics will be obstructed. So it would give a +1 here. It would give a +1. If you open your arm out, then there's a big suction. That would be a -1. So the average is 0. That's why that's like that. Okay. So the lymphatics make the counter adjustment. See right here. Here's the lymphatics and here's the capillary. Now, remember I said that if you have more water out than you did back in, you had more water out than you did back in, then that would be an angioedema, which could happen is if you had too much dilation of the arteriole, like in inflammation. Now, however, here's another term. That's angioedema, blood vessel edema. But if you had occlusion of the lymphatics, that's when you get lymphedema. You'll see that on TV. Somebody with a big leg and they're advertising. That's lymphedema. Okay? So edema can occur because of too much with the blood vessels, or it can occur because of obstruction there. Okay? So I just want to bring that up. So that gives you an idea of this net filtration activity we were talking about. And again, remember, let's go back to that it's for water coming in and out. That's all that's looking at, water coming in and out. And that's for that particular aspect there. All right. Now we can speak on the venules and the veins. The veins are our capacitance vessels, as we said. It's a blood vessel, the technical definition of blood vessel that returns blood back to the heart. There are different types of veins. The dependent veins, so first of all, let's talk about this. We have what we call superficial and deep veins. Superficial and deep veins. Come here, I'm going to make another slide. So what am I saying? We have what we're going to call superficial veins, and we have deep veins. Okay. The superficial veins are the ones located in the dermis and some of the hypodermis. They're superficial. The deep veins are deeper in. The superficial veins are smaller. The deep veins are bigger. If the superficial veins get clotted off, that's what we call varicose veins. They're very unsightly. The deep veins getting clotted off could give you that embolus we talked about in blood clotting, because they're big, and that blood clot, which would be a thrombus sitting there, could break free and go to the lung, killing you. So we have superficial and deep veins. We also have small, medium, and large veins. The small veins would be closer to the venules, and then they enlarge until you get to the giant veins, which were the vena cavas. Remember, the vena cavas entered the right atrium, the superior vena cava. Okay? All right. Then, if I talk about veins as far as if you're standing up location, the dependent veins are the ones below the heart. The superior veins are above the heart. The dependent veins are generally where you get your blood clots and everything because of venostasis and so forth. Okay? So the veins are formed from the capillary beds, postcapillary venules we talked about. Here veins formed when venules have thinner walls, larger lumens, thinner walls but larger lumens. If you recall, the veins were wider. Here we are. Let's look at that picture. See? Blood pressure is very low. There's hardly any blood pressure. They're called the capacitors vessels. Okay? We look here. So the veins have most of the blood. They have most of the blood. Okay? See, it's almost a zero pressure when you get to the veins. So therefore, the problem is, if it's a dependent vein, how do you get the blood back to the heart with no pressure in the lumen? It depends on external compression. See, veins have valves like lymphatics. So what you have to do is move around. You have to move around. That means if you stand in one place, it's trouble. But if you're moving around, you would squeeze down on it and squeeze to the next and squeeze to the next. That's why standing in a locked position for a person that has poor flow could cause blood clots. Need external compression and valves to get the blood back to the heart. If blood cannot get, you could get venostasis. This could lead to deep venous thrombosis in the deep veins or varicose veins in the superficial veins. Okay? Here's the difference between arteries and veins. Okay? All right. A vascular anastomosis is basically going to be, we'll go here, where several vessels come together. A vascular anastomosis is like where several vessels come together. Arterial anastomosis provides for collateral circulation. Collateral, we've talked about, means several routes to the same area, to compare it to an end artery. So end artery, when only one artery goes to an area. Okay? Collateral circulation is when you have several. Okay, so you can kind of look at that. All right, where we are now is the pulses, so we'll start another video.